All right, today is day 3 of binomial probability, which is one of the two types of probability we're covering in section 6.3 of our textbook. Okay, first couple slides, recap what do we know so far. All right, in order for a probability setting, oops, I'm sorry, we're not even zoomed in here. Zoomed correctly. There we go. Okay, in order for a setting to be considered binomial, we need to meet these conditions. The acronym BINS. Binary, each trial has to be classified as a success or a failure. Those trials have to be independent. We have to have a set number of trials, and the probability of success has to be constant for all of them. Okay, for the independent condition here, very often in real-world statistics, you are dealing with this in the context of sampling without replacement. In order to make sure that that condition here gets met when we're sampling without replacement, we have to make sure that our sample size is not more than 10% of the population size. Okay, given these conditions get met, we have our probability formula. This part right here, binomial probability formula. That part right there, known as the binomial coefficient, there are two different notations. Your calculator uses the NC on your calculator, that's an R instead of a K. The reference sheet, at least as it was last year, uses this for the AP exam. Okay, something that we mentioned last class, I believe, but didn't do anything to flesh it out, we're going to examine in detail today, that the mean and standard deviation of a binomial distribution is given by these formulas here. And we're using population notation because probability distributions refer to everything which has the connotation of being population versus sample. All right, be careful in the fact that these formulas are valid for binomial probability only. Don't use them where they don't apply. And for the purposes of memorization, you do not have to memorize these guys. They are given to you on the AP exam reference sheet. All right, now on to one of the new things for today. What we have here for the first graph in the upper left is a histogram of a binomial probability distribution where n is 10 and the probability of success is 8. So that's the number of trials is 10, probability of success is 8, and it has that basic shape to it. So it's not quite symmetric. It looks like it's skewed a little bit to the left. Now if we increase the number of trials from 10 to 20, now the graph looks like this. And if we increase it from 20 to 50, it looks like that. So it's certainly on the surface appearing to become more normal shaped as your n value increases. And not only does it appear that is true. That is a fact that as n gets increasingly large, the distribution becomes more and more normal in its shape. So what's going to happen here is if we have certain conditions being met, we can approximate a binomial distribution with a normal distribution. And right now, that may seem like, oh, well, who cares? But for the future, that's going to open up lots of options when it comes to dealing with some higher level statistics problems. All right, so tying together this idea right here with this idea, we have this. Suppose that X has the binomial distribution with n trials and success probability P. When n is large, the distribution of X is approximately normal with a mean and standard deviation of. So, when n is large, that mean and standard deviation of the binomial distribution become the mean and standard deviation of the normal distribution that we're going to use to approximate it. So, next question that gets begged here is, well, how large is large? Okay, as a rule of thumb, we use a normal approximation when n is so large that np is greater than 10 and 1 minus p is greater than 10. Okay, in other words, your expected number of successes and your expected number of failures are both at least 10. So, first thing is we have to know or assume or verify whatever is the condition for the problem that it's binomial. And then if it's binomial and we have this being met, we can approximate that binomial with the normal. So here's an example to tie all that stuff together. Sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. Suppose that exactly 60% of all adult residents would say agree if asked the same question. Let X equal the number in the sample who agree, and then estimate the probability that 1,520 or more of the sample agree. Well, the first thing we're going to do is verify that this thing is binomial. And we already know what the rules are, the bins, but what's an acceptable way to address it in context? Just listing the generic requirements are going to get you little or no credit whatsoever at all. So this is how you would word it. The B stands for each trial can be classified as a success or a failure. That statement by itself is generic. The specific thing you need to do for the context box to be checked is you have to state what's a success and what's a failure. In this problem, if you agree with that statement about shopping, it's considered a success. If you disagree, then it's considered a failure. I is the independence condition. Okay, in general, knowledge about one event or one trial can't give us any information about another trial. Okay, the specific thing that you want to address is if you're sampling without replacement, you have to talk about that 10% condition. Because the population of U.S. adults is greater than 25,000, it is reasonable to assume that sampling without replacement independence condition is met. So our sample size can't be more than 10% of the population size. So 10 times 2,500 is 25,000. Well, the U.S. population is certainly greater than that. Now, if it's a generally accepted known fact, like it's pretty much known by the reasonable human beings in the world, that the U.S. population is greater than 25,000. What if it was like 25 million, or it gets up into a number that maybe you're not quite sure? Then you would say something like, we must assume that the U.S. population is blah, blah. Okay, and we have to have a set number of trials. Meeting the context here is stating how many trials we have. S, the probability of success, has to be the same for each trial. In this case, we have to point out what the success was and what the probability is. All right, so we know it's binomial. Those conditions have been met. Next thing we're going to check. Can we approximate this binomial with a normal? So what we have to look for here is the expected number of successes, NP. Put in the numbers, what's the number? The expected number of failures, and 1 minus P. Put in the numbers, what's the answer to that? We have to specifically state that those are both at least 10. So for this type of thing here, you have to, at the very least, say how many expected successes there are, say at the very least how many expected failures there are, and then at the very least say that they're both at least 10. Ideally, you'd like to show a little bit of work with this. Some rubrics require it, some don't. Okay. Now, what we're going to do is get this answer two different ways. We're going to get it using the normal approximation. We're going to get it by using the straight up binomial probability. So, if we're going to do a normal approximation, that means we can use normal CDF. The mean and standard deviation are going to come from the mean and standard deviation formulas for a binomial. And recall that if you're doing a normal approximation, that means it's a continuous random variable, which means we're dealing with this as a density curve, which means that goes in as is. Whatever however it's stated in the problem, is the number that we put here, regardless of whether that was a greater than or a greater than or less, greater than or equal to. So, lower, upper, mean, standard deviation, you're looking at about a 21% chance. Okay, for the next slide, this is the exact same word problem. This just shows that normal work again. Now let's compare it to if we just did it as a binomial problem. So, x greater than or equal to 1,520. So we're going to use the fact that the sum of every possibility from 0 up to including 2,500 must equal 1. Then we're going to take away the stuff in the beginning that we don't want. What we don't want, actually let me label these things here, N, P, X. Number of trials, probability of success. If we want 1520 to the end, it means we want to take away the 0 to 1519. Now, if we're going to do this as a probability, a binomial probability, we're treating it as a discrete probability distribution, which means endpoints matter, which means we have to pay attention to what that x value is, depending on where it falls into the formula. So as a comparison, you can see the 2 decimal places of the nearest percent. It's the same approximation. It's about 21% as our final answer. The larger that n value is, the closer the binomial will be to the normal. The smaller the n value is, as long as we don't go past that success and failure thing being 10, the more of a discrepancy you tend to have. And that's just the nature of this is what it is. Although the formulas, that's an exact number based on this, the setting up of that is not necessarily an exact science. It's a little bit of an art, and there's an acceptable way to do that art work, but you're not going to have necessarily the exact same value here and here. That's just the nature of, that's the way it is in statistics. All right, wrapping up the comparison here. When we use the normal model to approximate the binomial model, we're using a continuous random variable to approximate a discrete random variable. So when we use the normal model, we no longer calculate the probability that a random variable equals a particular value, but only that it lies between two values. So even if the conditions get met in terms of approximating a binomial distribution with a normal distribution, you can't necessarily calculate all the same stuff. Specifically meaning, once we go to the normal, which is a continuous problem, you can't do the exactly so many successes. We only can do a range of successes. All right, today marks the end of basically close to 3 full classes of working with binomial distributions. This stuff that we just talked about here with the normal approximation, that marks the end of anything new. Under most circumstances, there's a day or two of mixed practice with what we've been doing. At the recording of this video, I'm not exactly sure how that plays out with our pacing for this particular school year, but as far as new material, that wraps up the binomial stuff rather, and we're moving on to some mixed practice with this. One more type of probability that we have to cover at the end of 6.3, and then that wraps up chapter 6 in our textbook.